we're going to record the analog of this, of what we're doing, and then it's going to get, I already did a video, it's kind of weird working backwards. There's a video doing it on the computer, okay? So I'm going to show you how to do it analog style, and then I'm going to attach it to another video showing how to do it in the Google Sheets with formulas, which is basically is the extent of my ability to use Google Sheets, okay? I'm pushing my abilities as far as I can. Before we get to it, we're going to do a couple basic definitions, so you have your notes out, right? Everybody's got your notes out, right? Because we come in, and I told you we weren't using a computer today, but you need to have your notes out. What? Okay. All right. The first graph on that paper is a speed time graph. And if you're assuming that there's no air resistance, something would be in free fall, right? If it's only gravity affecting it, it would be linear, okay? What's up? Speed time graph. Speed on this side, t on this side. If you're in free fall. So in your notes, you need to have the definition of free fall. Put it in your notes right now. If an object is in free fall, it by definition is not being affected by anything but gravity. Say again, free fall is defined not how we often define it in common language. How many of you ever heard like a James Bond movie or something? Oh, they're in free fall, right? That's not accurate. True free fall, there is no wind resistance, for example. No force is acting upon an object that's in free fall except gravity. Okay? And then we also have terminal velocity. Because a lot of times in common language, we say that it's in free fall. What they really mean is it's reached terminal velocity, so it's got steady speed now. And I'm going to show you on this really primitive speed time graph what that would look like. Okay? Terminal velocity, though, by the way, is reached when an object's momentum, a falling object's momentum, becomes equal with the force of wind resistance, the friction acting upon us, or upon it. In aerodynamics, I think they usually use like the word drag for that. Maybe a drag coefficient, right? That's over our head. What?
Drag race.
Drag what?
Race.
Drag race. Okay.
That's what
Okay.
my
Little different application of the word there. Okay, cool. So let's pretend we have not just a free-falling object, because if we're in Earth's atmosphere, it's impossible to have a free-falling object. It's not going to happen because you're going to have wind resistance. The closest you could get to it, have you guys ever heard of the Vomit Comet? Have you? So sometimes, like NASA will take up and train astronauts. They'll fly up and they'll nose down, and they will replicate free fall, because if you're inside of an airplane, the airplane is kind of taking away the wind rushing up in your face, right? Okay? But you're falling, so you feel like you're kind of like weightless. Does that make sense? And they go down and they go up and they go down multiple times. That's why it gets the name Vomit Comet, this 747 or for whatever they use. They'll also use it sometimes for movies where they want to shoot the movie and make it look like they're weightless. They put a green screen and do all that. They do it in a plane like that. Yes? Question?
I was gonna ask if that was like the sphere thing. Is it like the sphere thing that in like the machine they're like twisting around?
No, if it's spinning around, they're actually trying to increase or decrease the number, well, not decrease, the number of g-forces. So like if they're in the seat and they're spinning around, they're going to have more weight pushed on them. That's to replicate like when they take off in a rocket, they're going to have more than one g they're experiencing. So they want to know what that feels like before they actually take off and go to space. Does that make sense? Or also for like fighter pilots to figure out how do I cope with having the blood basically rush from my head, right? So if you're in a fighter plane, anybody watch like Top Gun or something, and they're pulling hard G's, the blood is going to want to rush out of your head. It's going to want to go down, right? Or if you're doing negative G, so if you're flying level and you just go down, the blood's going to rush to your head. So they have like G suits where they can where it applies force to their legs, for example. So if they're pulling positive G's, the suit will actually squeeze their legs to keep blood from going down. Kind of like hold it up. It helps them not to black out. Yeah. Anyway, related but different. Let's get back to this. If we are, let's do a parachutist. Let's do a parachutist for an example. If we are a parachutist and we are going to fall, we'll say our vertical speed, our falling speed. So you're traveling along at whatever speed on the airplane. We're not going to count that, though. We're just going to say the speed of the fall. Is that everybody tracking? Okay. It would start at 0. If there were no wind resistance, your acceleration would just continue forever until either you deploy your chute or you hit the ground. Agreed? Okay. But it isn't going to be perfectly like that, because as you're accelerating due to gravity, you'll also start to lose a little bit of that acceleration the faster you go because of the wind resistance. Okay? So what will happen, there'll be a curve, there'll be almost no wind resistance when you're going very slowly down, and then as your speed picks up down, you'll have more resistance of the air coming up at you, right? Okay? So there will be acceleration, ACC for acceleration. There will be increasing wind resistance as this starts to curve, and then finally there will be a point where the line on our speed time graph is perfectly horizontal, which means you have reached terminal velocity. At this point right here, you will have equal force, what did I say? The falling object's momentum, the force of that object falling would become equal with the wind resistance. At that point, they've reached a steady speed. They will continue to fall at that speed until either they deploy their chute or they hit the ground. So what you'll see, okay, you're flying along in the airplane, time doesn't stop. You start to accelerate. You're still accelerating, but the wind resistance is slowing your acceleration, and then finally there's no acceleration. You're just traveling at a steady state down, and then they pull their chute. As soon as they pull their chute, there's going to be a drastic deceleration, okay, until, it'd be pretty short too, actually, as far as the time, so it would be pretty steep. And then it would balance back out. So you have chute deploys right here. It slows your descent down until you reach a new equilibrium, a new terminal velocity with the chute. Does that make sense? So now you're traveling at a much slower speed down, and then what would happen when you hit the ground, you'd have a very rapid, man, this marker is dying, a very rapid deceleration to 0. That was on me. Are you okay? You awake? Cool. All right, moving on. Are there questions on this? I know it's an ugly, ugly graph, but does it make sense? That's what I'm worried about. Okay, yeah. It's pretty. Y'all are super nice. All right, moving on. I want you to make this would be called a table, right? And we're going to put a few planets. Earth, Mars, Jupiter, and the now classified as a dwarf planet, Pluto. No, it wasn't destroyed. Nope, nothing happened to Pluto. We know more about it now, but anyway. And then you're going to make rows for each of those. That's not looking too bad. Do you remember this page in the workbook where it said, hey, what would you multiply your weight on Earth by to find your weight in newtons on Pluto? Remember that? Yeah. And that's the only thing we used it for. Oh, you multiply by 0.7%. Done. I like that chart, and I want to do more with it, so that's what we're doing today. We are going to use what they give us, and they give us a multiplier. So the multiplier is the number by which you will multiply your weight in newtons on Earth to get your weight in newtons on that other planet. Does that make sense? Okay? And they give those to us. Now, Earth would just be 1, because your weight times your weight is your weight on Earth. Mars was 0.38.
Wow.
Jupiter was 2.36. And Pluto is 0.007.
Wow.
Yeah, you're going to be light on Pluto.
I'm jumping a mile.
0.38 is just a little bit more than a third, right? So we're just in your mind be thinking, well, my weight's going to be just over a third of what it is on Earth, and Jupiter is 2.36 times as much. So if I weigh 213 pounds here, I'm going to be, what, close to 500 pounds? Something like that?
Could I go do the long jump on
Yeah, you're gonna
Pluto?
be.
Yeah.
You're gonna be.
Yeah. No, that's a good point. So he said, could I do the long jump on Pluto? So think about this. Think about this. If you were to jump straight up, if I jump straight up, I can touch the ceiling. You want to see it?
Yeah.
Okay.
Yes.
There, I did it. I probably showed my boxers or something. Anyway, so I can touch the ceiling, which is probably what, 8.5 feet?
Well, I feel like 9 or something.
And 9 tops.
How tall
I
are you?
cannot dunk. If I'm in my athletic attire, I might be able to barely touch the rim. Okay, barely. So anyway, if I did that same jump on Pluto at 0.007 of the gravity, I'm thinking I'm jumping hundreds of feet in the air.
You're probably not gonna come back down.
So think about good
Yeah,
point.
but
Like,
it's crazy
at
that
what point
most
am I
of it-
going to be able to reach escape velocity? Not. But I'm going to jump a few hundred feet in the air. So here's the question for you. If I jump a few hundred feet into the very, very thin atmosphere of Pluto, what goes up is still coming down because I didn't reach escape velocity. How's my landing going to go?
Very soft.
No more.
No, actually, I think you'll be like light on
No,
your feet.
because you have less gravity.
Yeah.
Think about this.
Are you coming down?
On Earth, when I jump up and then land, the amount of force exerted upon my musculature to jump and to absorb the impact is about the same, is it not? It's the same on Pluto. So even though I'm able to jump a couple hundred feet in the air, I'm also able to tolerate the impact because it's the same amount of force, or very close to it. Does that make sense? Okay, cool. So that's a sidebar conversation, but it's interesting. I'm glad you two brought those things up. All right, so we have the multipliers. What else do we already have? We also know the acceleration due to Earth's gravity. Do you guys remember? We just talked about it. They rounded it to 10. It's actually 9.8 meters per second squared. So I'm going to say acceleration due to gravity. Okay? So it's 9.8, and that's going to be in meters per second squared. Getting kind of tucked under the TV. I hope you guys can see that. And so that's going to be our next column. That's known. We know this. I also can very easily find my weight in newtons. Because we've done that before in class, haven't we? We're going to have to do it again.
No.
No.
What if I remember
Not
your weight?
math.
What if I remember?
If you
your
remember
weight?
it, you remember. That's cool. But we're still going to have to convert to get our mass, unless you remember that as well.
I don't remember.
I don't remember.
He's gonna explain.
Yeah, we're going to go through the whole
yours.
thing. Absolutely. All right. Am I going too fast?
No.
Yes.
All right, cool. If at some point I'm going too fast, go ahead and stop me. But if you're not paying attention, it'd be very easy to miss something, and then you say you're going too fast. Well, I'm not going too fast. You're just not following along. Okay? So let's balance that. All right, so first thing we need to do is get my weight in newtons on Earth. Okay? So I'm going to take my weight in pounds, 213, divided by 2.2. You take your weight in pounds times 2.2, or excuse me, divided by 2.2 to get your mass in kilograms.
Wait, so we were divided by 2.2?
Yep. So I'm going to take 213 divided by 2.2. You're going to take your weight in pounds divided by 2.2. I get 96.8 kilograms. Okay? Where's yours? Where's your calculator?
I don't have one.
Do you have a phone?
Nope.
Oh. Do you have a computer?
Yeah.
You could use it, but you got that one. That's fine. I think I've got another one. I think I've got another one. All right. All right, is everybody there? Do you guys need a second? All right, so we have our mass. Now what we need to do is go from mass to weight, because our mass is the same no matter where we go, right? But our weight is going to be different on different planets because there's different acceleration due to the force of gravity. All right, here we go. So force is equal to what? Mass times what? A change in velocity is what? Acceleration. Okay, so stop. Just stand for it. Thank you. All right, so force is equal to mass times acceleration. Do we have our force? No, we're looking for that, right? We're looking for force, which would be our weight due to that gravity. Do we have our mass? Yeah, we just found that, right? We took our weight in pounds, divided by 2.2 to get kilograms. So I can put my number in here. You guys should also put your number in. So I put 96.8 for me, and I'm going to leave that A there for acceleration.
Do we write this down?
Yeah.
Like our...
Yours.
Okay.
Use your numbers, don't use mine. But don't I also know acceleration due to Earth's gravity? I've got it. So I can plug that in. 9.8 meters per second squared. Cool. Now I just take this number times this number to get my weight in newtons on Earth. So I'm going to take 96.8 times 9.8. Those are my numbers. You do your mass times 9.8. So my weight is going to be 949. And that's in newtons.
Wait, how do we do that again?
You're going to take your mass times 9.8.
420? No.
Okay, so the next thing we got to do is we have our weight in newtons on Earth. Are you paying attention?
Yep.
We're going to take your weight in newtons on Earth times the multiplier for each planet to get your weight in newtons on that planet. So I will take 949 times 0.38 to get my weight in newtons on Mars. You're going to do that for each planet. Multiply your weight on Earth in newtons times the planet's multiplier to get you the weight on that planet. Go ahead.
Honestly, there's a lot of math going on in science class.
So you're
Yeah.
going to let us round up?
Yep.
I like this. I'm good at math.
The last thing we're going to do, and I'll show you the process for Mars. The process will be the same for the other planets as well. We are once again going to be using our force equals to mass times acceleration formula, but we're going to be looking for acceleration now. We have these three values that we don't have: the acceleration due to gravity on Mars, on Jupiter, on Pluto. Earth is 9.8, we have that, but we need to find these. So we're going to work kind of backwards, but it's still super simple math, all right? So do we have force for Mars? Yeah, your weight on Mars in newtons is a force value due to the gravity on Mars. So we're going to take our F is going to be 361 for me. That's my weight. You put your weight right here for force. Do we have our mass? Yes, we converted our mass from pounds to kilograms, right? So I'm going to put in my mass. For me, it's 96.8 kilograms. And then we multiply by acceleration to get our force. Okay?
You get 96.
96.8 is my mass.
Oh, yeah.
So you're going to have your weight on Mars in newtons is equal to your mass times acceleration. All right? And then what we're going to do is you're going to divide both sides by 96.8 by your mass.
Oh, okay.
Okay? So you'll have your weight in newtons divided by your mass. And what does that do to this side? It gets rid of this, right?
Yep.
All you'll have left now is acceleration equal to the answer.
Yeah.
So you take your weight in newtons on Mars divided by your mass, and that's going to give you acceleration what? Yeah.
Good job.
You got it?
What did you get, Aiden? How did you get 9 points? I think you did something.
And I get 7.3.
Yeah.
Wait, I'm backwards. 3.7.
Yeah, I was
I'm
like,
pretty sure I'm
wait.
not
I got
dyslexic, but I just
3.7.
did it.
Mr. Hansen, I got 3 points.
You don't say. Yes,
Yay.
why?
Oh, it's the right.
Because acceleration due to gravity on Mars is going to be the same for all of us.
everyone, yeah.
Yes. So we should all, meters per second squared, all of you, you might be off a little bit, but you should be very close to 3.7 meters per second squared for your answer. And then we'll put that right here. Do you see the process that you're going to do for the next one? So for Jupiter, you're going to take your Jupiter weight divided by your mass will give you the acceleration on Jupiter.
Oh, Jupiter. I was thinking Earth.
And then you'll do the one for Pluto.
Oh, yeah, that's what
You're doing one planet at a time.
Oh, so we're gonna do the same thing.
Yes.
So, okay, all right.
You literally just take whatever your newtons are on each planet and divide it by what's your
999.
Yep.
What?
Because your kilogram mass is a constant.
Divided by that? Wait,
Yep.
hold on.
Look,
Oh, I did
look
mine.
right here.
I multiplied.
Look right here. Your weight in newtons divided by your mass
Got it.
gets you the acceleration. So finish those up. You'll have a very similar number to mine here because while our acceleration due to gravity on each planet applies evenly to all of us, we all have different mass. So the acceleration due to gravity on each planet is the same, but our mass is different. So the force of gravity is not the same for all of us. Does that make sense? Because force is mass and acceleration multiplied by each other, or with each other.
What if my mass on Pluto was like 500?
Your mass on Pluto would be the same as your mass on Earth in kilograms, right?
Yeah.
Mass is not the same as weight.
I love how your eyes went like.
All right, so this is like part 2. We did the classroom portion. Here we are. I'm going to use a spreadsheet to do a lot of the same things. You can see this looks similar kind of to what we did on the board. And we have basic information filled out. We have the multipliers for each of the planets. So you would take your weight in newtons on Earth, for example, and multiply it by 0.38 to get your weight in newtons on Mars, and so forth for each of the other two. We're also going to use force equals mass times acceleration to get the acceleration due to gravity for Mars, for Jupiter, for Pluto. And I'm going to try, I don't often use sheets for this sort of thing, but you can use some formulas to show it in here. Okay, and this hopefully will translate to some of the other things that you might use sheets for. So without further ado, first of all, we've got to get our weight in newtons on Earth. I keep looking at the camera here. I guess I could put it closer to where you are up there. But so first thing first, what do I weigh in pounds? Because I'm an American and I don't know my weight or my mass in kilograms. So I'm going to say 213, that's my pounds. The formula is pounds divided by 2.2. So what I can do, if I want to get technical or
overly using the sheet, this is how you do a formula. So you use equals, and that lets the computer know that you're going to do a formula. I'm going to have 213, but I don't have to write in 213. I know it's not going to save much time, but I'm just showing you how to do it. A11 is this box. So I type in A11. It says, oh, the value from this box, and then I'm going to say divided by 2.2. Enter, and it gives me my mass in kilograms. That's what this is. Also, just a side note, if you click on this and you got all these extra decimals, if you come up here, bring that down to like 1, maybe, okay? Or whatever you need for your application. Then I can use this and drop it into my force equals mass, 96.8, times acceleration, which is 9.8 meters per second, or 96.8 meters per second squared, or 9.8 meters per second squared, and see what we get. So let's see, can I do something swoopy with that? Well, I could take, I'm looking for force in newtons, so it's going to be mass. So it's going to be the value from B11. Oop, gotta get my equal sign there first. Come on now. There we go. And if I just do that, it just gives me the value. But then I want to multiply it by P11 multiplied by the value for B2. And I get my weight in newtons on Earth. And again, I'm going to trim that down. All right. Now that I have that, I can use the multiplier to find my weight in newtons for Mars, Jupiter, and Pluto. So again, I'm going to say equal. This way I don't have to open up a calculator separately on my screen here. So I've got equal D2 times C3, which is this box. Enter. Does it for me right there. And again, there we go. I could do them all and then highlight this and say, hey, drop those back, those decimals back. All right. And now I'm going to say equals, same again, D2 times 4, C4, not the explosives. Oops. There we go. And that's a heck of a value there, isn't it? And check this out. I love this. This is so cool. It's trying to anticipate, saying, well, based on what you're doing here, is this what you're wanting to do? So I'm going to see what the formula is. It said D2. Do you want to do D2 times C4? Well, that's what this one was. So I don't know what they're doing here. So no, I don't want that. I want D2 times C5. So equals D2 times C. Oh, suggested. Look at that. And that is the right value. And now I'm going to take both of these and drop them back. I'm going to leave this one at 6.6, but I'm going to drop this one all the way back to 220 or 2239. All right. Now we have, let me get that centered. And why is this a different font now? Anyway, there we go. We've got all our weights in newtons for Earth, Mars, Jupiter, Pluto. Cool. Now we're going to do the last piece for each of these, which is to fill in the acceleration due to gravity. We're looking for A. We have force over here. We have mass, your mass, right? And so to get A by itself, to be able to solve for A, we need to divide both sides by mass. So I know it'll be this value divided by this value to get me this value, okay? And you can see that's what happened here with Earth. There's my force divided by my mass would end up getting me back to 9.8. And let's prove it. Let's prove it. We should end up getting close to 9.8. Now, it might not be exact, but it should be close with rounding. We're going to say D2, and we're going to divide by B11. And I love how it highlights it for you to make sure you're in the right box. Enter, and it goes, wait, reference. Something went wrong. Let me back up. Something definitely went wrong. Let me delete this. Oh, I was already using that value, so I can't change that. So that's all right. We'll leave that, and we'll just do it for these. So I'm going to take my D3 equals D3 divided by my B11, enter, and I get 3.724. I'll drop that back here in a second, and that makes good sense, because if our weight is 0.38, this looks like just over a third of that value. So yeah, that makes sense. It passes the sniff test. And then here we're going to say D4 divided by B11. And here we're going to say D5 divided by B11. And we're done. I mean, we've got all of our accelerations due to gravity. I will take these two and drop the decimal value back to the 10th space. I'm going to leave this one here, obviously, because I would round up to 1, but that's 30% off of 1, so or 0.1. So we'll leave it like that, and that's it. So let's see. Today we did it on the table, on the board. We talked about free fall versus terminal velocity. We did a little weird graph on the board, and ugly graph, but it works. It demonstrates the point. So, and hopefully you learned something about how to use Sheet. A lot of you haven't used this much. So I haven't used it much, and it's been years and years and years since I did much with either Google Sheet or with Microsoft Spreadsheet. But anyway, have a good day. If you have any questions and you're a student of mine, ask me in class, okay? If you're not a student of mine, but you have a question or you have a comment or a suggestion, maybe let me know how to do something a little more efficiently or easier other than just practice. Put it in the comments. I'd appreciate it. Have a good one.